Good everybody, here you are once again. This is Turning Points tutorial, and we have come to another section in our chemistry class. And you know we're dealing with Chem 001. We want to proceed from the place we stopped before. Remember, we have been handling the topic oxidation number, and we have dealt with various types of calculation based on oxidation number. But now we want to see, just to remind you once again, just take this question. I know if you were on your own tried to answer some kind of question, some past questions, and then you should be able to answer this. Let me just give you a test as a kind of continuation. Let's look at one or two examples again. For example, if you are asked to find the oxidation number of this sulfur in this set or sulfur in this compound, now you have this very compound before us, and I know you should be able to call the name of this compound. But you know that one of the importance or one of the uses of oxidation number is to help us to actually call or write down the IUPAC nomenclature of inorganic compounds. So let's just see. To call this one, you can see you try to say sodium heptaoxo, then sulfate something, or you can say sodium heptaoxo, but how can you not call the other names when you, or the other part of the name, when you don't know the oxidation number? That's another problem. So let's see here. In the very compound, you know quite well that there is no charge here, there is no charge. And since there is no charge right now, the very place, it simply means this compound is a neutral compound. Therefore, everything equals 0. And you know quite well that sodium in its combined state is always plus 1. Oxygen in its combined state is always minus 2. Then, what you need to do right now is to work on this. You are looking for the oxidation number of sulfur. Then we go this way. You have sodium being plus 1. Then you have plus 1, then in brackets, then the subscript here is 2 times 2. Plus, then you have sulfur. Sulfur is the case study right now. Sulfur is the target. We are looking for the oxidation number of sulfur. So we say times sulfur times 2 plus, then we have the next aspect, which is oxygen. And you know quite well that in the combined state, oxygen has an oxidation number of minus 2. So take it down like this, minus 2, then times 7, all equals 0. Now let's go back this way. Looking at this side, you have plus 1 times 2, that gives us plus 2. Then plus the sulfur times 2, that gives us 2 sulfur. Then plus minus 2 times 7 is 2, 7 times minus 2, that gives us plus minus 14. All equal to 0. Let's go back again to this side. Then you continue. It implies that plus 2, then plus times minus is minus. You know quite well that plus 2 plus 2s, then here it changes to minus. So plus times minus, you have minus 14 equals 0. Then rearrange everything. Taking it to the other side, you have 2s plus 2s equals 0. Plus 2 crossing over, you have minus 2. Then minus 14 crossing over, you have plus 14. Then at the final analysis, you have minus 2 sulfur, plus 2 sulfur. 0 minus 2 is going to be minus 2. Then minus 2 plus 14, that gives us plus 12. Then finally you have sulfur equals plus 12 all over plus 2 here. Then you will divide. When you are through the division, you have plus 6. That is the oxidation number of sulfur. So you can see here, when you go through everything, you find out that the oxidation number of sulfur is plus 6. Then let's have a look at this. The next one. Let's say you are given something like this, MnO2 or MnO4 ion, that is tetraoxomanganate something. You don't know how to call the name. Right here you have sodium heptaoxo sulfate. Then you can say sulfate 6 because its oxidation number of sulfur is 6. So then To the other side, you have the same thing now. You are asked to find the, let's now look at it very well. Manganese is the case study right now. We are looking for the oxidation number of manganese. And you can say tetraoxo as 4, tetra, so that refers to 4, tetraoxo, then manganese, then you have manganate what? You don't know. Then once you do the calculation, this is an ion, and there is a charge, minus. This minus means -1, so you can equate everything to -1. Since the charge here, the charge everything here is minus, so you have everything equals -1. I believe you are getting it clearly. Then the next thing to do right now, you're looking at sulfur as manganese, and it lies here that manganese plus, then oxygen in its combined state has -2 as the oxidation number. You have in bracket -2, then you have 4 times 4, all equals -1. Then look at this very well. -2 times 4, that gives us, just open the bracket, -2 times 4, you have -8. And then it implies there that a manganese plus the open bracket -8, close the bracket, equals -1. And then you can say, let's move forward to the next stage. Plus and minus is what? Minus, and then you have manganese plus what? -8. You can have equals -1. Then you go to the other side, you have manganese equals -1 plus 8, and that gives us +7. So we can see here that the oxidation of manganese is +7. Now you understand now that you can call the name tetraoxo manganese what? Manganese 7, because of the kind of the oxidation state it has, +7. So you can say manganese 7, tetraoxo manganese 7. That's the, but this one is not honorary. Just it doesn't end as an ion, it's a radical. So you can say tetraoxo manganese 7 ion. Then let's move to the next stage here. We discuss issues concerning oxidation number, and we have talked about the issue based on the how to calculate, make our calculations. But what we now do right now, we take a look at the uses. Why is it that we consider this issue of the oxidation number? Why is it so important? Because of the uses. It has so much uses. Now let's come back to the uses of oxidation number in any chemical reaction or in chemistry. Uses of oxidation number. Number 1, it can be used in writing the chemical formula of a compound. You can use it to write the chemical formula of a compound. Take for instance, you have here, if you have this radical CO3 2-, and you have, for example, this one here, and then you talk about another radical like let's say aluminium 3+. This is the cation, and this is the anion. You want to write the chemical formula of aluminium triisocarbonate 4, then you can just say this is this 3+ and this is 2-. You bring it together side by side, or you can say aluminium 3+ triisocarbonate 4 ion. Then you will interchange. Then after, when you interchange, as you take the charge here, the value close to the charge, and write it as a subscript of the anion side, that is the negative side. You write it down 3. Then take this one you're seeing here, and that way of doing it, you can use to do you can write another pattern to follow. Take the number that is attached to this charge here, and then write it down, and you have what? Look at it right now. Do something now. 2 times +3, you have +6. Now 3 times -2, you have -6. This 2- means -2, and this 3+ means +3. Then you can just do the multiplication. When you are through the time scene, you have +6. Through the time scene here, you have -6. +6 -6, that gives you 0. So the charges are now equal and opposites. You can wipe them out. And at the end of the day, the formula is aluminium triisocarbonate 4. Aluminium triisocarbonate 4 is the formula. Aluminium triisocarbonate 4. And then if you want to write, for example, again, let's say you have the sodium, or can say calcium hydroxide. Calcium hydroxide as a case study. This calcium hydroxide is made up of two cations. So sorry, two ions. One is a cation and one is an anion. The cation is a calcium 2 plus, while the anion is hydroxide ion and it's OH minus. Bring them side by side, you can see Ca2 plus and OH minus. Then the minus means minus 1. You write the minus the 1 here, take the 1 and write it here. Then for the 2 plus 2, which is 2 plus, you take the 2 and then put it in bracket. This is negative side. Bracket, place it in the bracket, and then take the 2 and put it as a subscript. When you have done that, you say 1 times plus 2 is plus 2. 2 times minus 1, that is another minus means minus 1. Then you can say minus 2. Then plus 2 minus 2, that's 0. So the charges are equal and opposite, neutral. Then you can write Ca1 means Ca. Then OH in brackets, then you have 2. So this is called calcium hydroxide. Calcium hydroxide ion. This is the right formula, so you don't have to go this way and say this is the formula for calcium hydroxide. It's wrong. So when you do this kind of balancing, you have the right formula. So you can see one of the uses is what? Number 1, like I said before, it is used in writing the chemical formula of a compound. Number 2, it is used in the IUPAC nomenclature of inorganic compound. IUPAC nomenclature of inorganic compound. How can we write the nomenclature, the IUPAC nomenclature of inorganic compound? You want to go the way the pattern we apply in organic chemistry. You make some mistakes. But when you are used to writing, or you know how to apply, or you see one of the uses of oxidation number, then it will help you very well to write the IUPAC nomenclature of inorganic compound. Number 3, it is used to predict the position of an element in a periodic table. Now, when you come to this aspect, the next thing we'll discuss right now is balancing of redox reaction. We want to give you some issues, some things you must know when you consider the aspect of balancing of redox reaction. Before you talk about the balancing, get to understand that the balancing of redox equation is just like you can say, okay, how can we apply it? It's always done in a medium. It's always occurring in a medium. That is, it can either be in acidic medium or in alkaline / you can say neutral medium. Now, when you are balancing a redox reaction, you will be asked in your exam to balance it in acidic medium, or you can balance it in alkaline. Alkaline means base, or it's a base, or / neutral medium. So there are two media to actually carry out the balancing. It's either you will do it in alkaline / neutral medium, or you can carry it out in acidic medium. Then the next thing to understand is the type of products that you expect to have at the end of the balancing or at the end of the redox reaction. It depends largely on the medium in which the reaction takes place. So, for example, now if you have in acidic medium, you pick up an oxidizing agent like we use this thing before, MnO4 ion. This is an oxidizing agent, and if MnO4 ion is reacting with a reducing agent, because MnO4 ion is an oxidizing agent itself. When it's reacting with a reducing agent, at the end, if it occurs in an acidic medium, what will happen? You know quite well that MnO4 ion is purple in color. So what happens that in this reaction, when it occurs, what happens? At the end of the day, something happens to MnO4. The MnO4 is being reduced by the reducing agent. The MnO4 itself is the oxidizing agent, but the reducing agent takes away the oxygen and then it's being reduced to the Mn2 plus, that is manganese 2 plus ion, and then at the end of the day, that is where you have other things. Then look at it very well now. From this side, it changes to colorless. This one becomes colorless. If it happens in acidic medium, purple color of MnO4 ion changes to colorless. That is in acidic medium. What if it happens in basic medium? If MnO4 ion is actually reacting with a reducing agent, and it takes place in a basic medium. Basic medium means alkaline medium or neutral medium. Neutral or alkaline medium, then what happens, instead of changing from purple to colorless, then it changes from purple to brown, and this is the result, MnO2 manganese 2 ion, and so manganese 2 oxide, and so for in this kind of reaction, you can say because it occurs in a basic medium, that is alkaline/neutral medium, then you can say that the kind of color change will now change from purple. The color change now is from purple to brown. This is a brown. This compound has a brown color, and so that's why I said before that the kind of redox reaction, the kind of product that you can get at the end of a redox reaction depends on the medium in which the redox reaction takes place. If it actually occur in alkaline, for example, like this one, if it occur in acidic medium, it changes from purple to colorless, from purple to colorless. Then if it occurs in alkaline, that is basic/neutral medium, alkaline/neutral medium, then it changes from purple to brown, and this is the result. This is the product. Now, this one tells us that this aspect of balancing, the balancing of redox reaction will always be based on this medium, acidic medium, or based on what, alkaline/neutral medium. That is based on basic medium. Now we want to go to the other aspects. We want to move to the other aspect that has to do with the steps to follow. But if you consider it very well, when you are balancing a redox reaction, we use different methods to carry out the balancing. One is either by inspection, two is either done by mathematical method, three is either through the half cell method, or you can say half equation method, and three is done by, number four is actually carried out either by the oxidation number method. So we want to move now to the other stage, the balancing of redox reaction, the steps to follow. Then we'll go on to the calculation. Let's continue. Now we move on to the balancing of the redox reaction or redox equation. Before then, let's consider the steps. Because we are dealing with the balancing of redox reaction. What are the steps? The steps to follow. Number one, split the equation, or you can say split the cell or the equation into two half equations or half cell. Then after that is you should kind of separate two of them into two different half equation. Then you call one of them oxidation reaction or oxidation half reaction, then the other reduction half reaction. And when you have done that, the next thing, number two, the next second step is by inspection, balance each of the half equation in respect to the atoms and charges, and then the atoms are balanced in a special order. The atoms should be balanced in a particular order. Now that is, you start with the central atom. After that, then you balance the oxygen. Then the last thing to do is to balance the hydrogen. I said the balancing should be in a particular order. First of all, you start with the central atom. Then after that, you go to the aspect of balancing the oxygen. Then when you are through with the balancing of the oxygen, then you can go to the balancing of the hydrogen. Then in this aspect, what you should do now is to balance oxygen or the hydrogen in any of the medium. You must take note of the following steps. You must understand that there are some principles you should adhere to. The question is it going to be in acidic medium, or will it be in basic medium, that is alkaline medium, or in neutral, that is a neutral medium? Then if you are to balance it in acidic medium, then what you're going to do right now, one H2O is used to balance up each oxygen atom, and one hydrogen is used, as one hydrogen ion is used to balance up each hydrogen atom on the deficient side of the equation. That is, let me go again. In acidic medium, one H2O is used to balance up each oxygen atom. And then again, at the same time, one hydrogen ion, that is H plus, should be used to balance up each hydrogen atom on the deficient side of the equation. This means that the side that lacks oxygen, you use what? H2O to balance up that side. the balance of the oxygen at that side. Then the side that lacks hydrogen, you use hydrogen ion to go and balance of that the balance of the hydrogen at that side. Then the next thing to do, if it's not in acidic medium, then if it's in basic medium, that is neutral medium, that is alkaline medium, what you should do is that 2OH minus, that is OH minus, that is 2 hydroxy ion, is used to balance up each oxygen atom, and 1 H2O, that is 1 water molecule, is used to balance up 2 hydrogen atoms. It's used to balance up 2 hydrogen atoms on the deficient side. That means the side that is actually lacking. Then that is in the case of what? In the, as a basic medium, as the alkaline medium. Then in both acidic and neutral medium, electrons are used for balancing up charges. You use electrons. They are used for balancing up charges. Then in step 3, by multiplying each of the half equation with the appropriate factors to balance the number of electrons, this one is done in 2 half equation. You use the electron, that is, if you pick up the electron in the first half equation, that is, then you pick it up after the balancing is over, then you pick the electron in the first half equation, used to balance that's the coefficient of that electron, used to balance up, you multiply, do a kind of multiplication. So you used to balance up the other one, then the electron in the second half equation, pick it up, that what you call right now, the number behind it, what you call, you pick it up, that's the coefficient, used to multiply the first equation. Then after that, then you do a kind of combination, add up the 2 balanced equations, that is the reactant to the reactants, then product to the product side. And you do a combination. After that, you look at both sides. After the union, the resulting equation, look at both sides, check if you have electron on the left hand side and electron on the right hand side, you cancel them out. Then if you have cannot say, let's say a hydrogen ion at one side and the other side, you cancel them out. You do it systematically, mathematically. Then look at the hydroxide ion. Is there anyone at the left hand side or the right hand side? If there is anyone, then you cancel them out. Then check out for H2O. That is water molecule. If you find it at the left hand side or at the right hand side, and at the right hand side at the same time, you cancel them out mathematically. It as if they appear on both sides. Then after that, if there's any form of fraction, if there's any fraction left, if there's any fraction in the equation, clear all fraction to have a simple balanced equation, balanced redox reaction equation. You have a simple balanced redox equation. So these are the steps to follow. First one, I said split the equation into 2 halves. That is called it half equation, half equation. Then one is called reduction equation. Then the other one is called oxidation half equation. Then number 2, you by inspection you do the work of balancing. Start by balancing the central atom. Then you go ahead and balance the oxygen. After that, balance the hydrogen. And this one is done in both either in acidic medium or basic medium. When you are done with the issue of balancing as in acidic medium or basic medium, then go to step 3 by multiplying each side with the appropriate factor to balance the number of electrons in the 2 half equation. You pick up the coefficient of the electron in both equations, interchange, and then do your multiplication. Then finally you add up the 2 equations. Then you do your cancellation where necessary. If there's any species that is occurring on both sides, you cancel all those species, and those species are electron. It can be electron, it can be hydroxide ion, it can be H2O, that is water molecule, or hydrogen ion. If there's any of these species, then you cancel out on both sides, then you have a perfect balanced redox reaction or redox equation. So these are the steps. Now we want to go on to, in our next class, we will now see how we apply that. So please, on your own, this is 20-point tutorial. Find out any redox reaction that is not balanced. Try to follow the steps and then do the balancing. If there's any problem, you can call us on call our number or go on WhatsApp and then chat with us how you can go about that. But in the next class, we shall see various examples how you can do the balancing in acidic medium only first. We will see you in the next class. Thank you.